Hello, everyone. Today is July 1st, 2022. I'm here today with Aaron Meyer. Aaron is a postdoc at UC Berkeley. Thanks for coming on the podcast, Aaron.
Oh, yeah. Thanks for having me.
You're welcome. So what is your postdoc at UC Berkeley?
So postdoc is short for postdoctoral. So I have a PhD, and now this is kind of the intermediate stage between being a graduate student and being a full professor with a permanent position. So I'm still quite young, moving around, learning from several groups of people.
What were you learning in your PhD program?
Yeah, so actually I should start in undergrad. In undergrad, I had a research position where I was actually helping to code some simulations. So these are called Monte Carlo simulations, trying to elicit some visions of gambling at Vegas or something like that. But really, it's a simulation where you're trying to create some fake events. So say you have a detector, you want to measure some sort of particle going through it, you would come up with some simulation that simulates this particle going through the detector, what responses the detector has, and how much you could measure this. So the idea is that you can understand your detector better by doing these simulations. So I started out doing this in undergrad, and then when I got to grad school, my project just kind of branched off of that. So the simulations that I was doing were for neutrino physics. So neutrinos being a type of particle that are created a lot by the sun, they're associated with radioactive decay. And so there are some neutrino oscillation experiments which are ongoing. And part of the problem is that neutrinos are very weakly interacting. So they are very difficult to measure, and you end up having a very hard time measuring their interaction strength, essentially how many times they'll interact. So coming up with better predictions for that requires some other inputs. You can get those inputs from doing experiments, but the method that I was using was purely based on theory, using the most sophisticated theories we have that actually make predictions, and trying to come up with some predictions for how strongly these neutrinos interact and how many events we actually expect to see in these detectors. And so from grad school, my research has just been based on this theoretical concept, which is called Lattice QCD. It's a computational method for trying to assess these interaction strengths. And so that's currently what I do, is I simulate these types of interactions on a computer, and then I use that to make predictions about the interaction strengths of neutrinos. So in a nutshell.
In a nutshell. That was a big nutshell.
Yeah.
So were these simulations you were running in undergrad also revolving around neutrinos?
They were, but they were more simulating from the a different side of things. So it was less theory-based and more just an ad hoc. We are trying to come up with some sort of description of the data that is reasonably close to what we actually do expect.
Okay. And when you mean ad hoc, you weren't running Lattice QCD simulations with C++ and various other languages?
Yeah, this is still C++, but it is not Lattice QCD. Lattice QCD is an entire industry on its own. And so these other calculations were purely just, when I say ad hoc, I really mean we're trying to come up with a fit function that describes the shape of the data that we're seeing. And so it might not necessarily have a completely well-based theoretical underpinning, but it describes the data well enough that it reproduces the physics that we want to see. So you're really looking for something that's quick and dirty and can reproduce what you want to see beforehand. And the idea is really just to get a rough estimate of what you're going to see in your detector, rather than having the full theoretical description, which may take a long time to compute and end up being completely unusable in terms of what the experiments need.
And that was what that full description was what you were developing at in your undergrad.
That's correct. Yes.
Okay. And the difference now is that you're not running a single project with a single theory anymore, or you weren't for your graduate studies. Is that correct?
For my graduate studies, there's a lot going on. Sorry, for now, there's a lot going on. For my graduate studies, I was focusing specifically on one problem, which was to try to narrow the scope very dramatically to just looking at the neutrino interacting with a single nucleon, which is a simplification of the actual full scope of things that you can see in the detector when you have a neutrino oscillation experiment, for example. So I was specifically looking at the interactions of a single nucleon and doing billiard ball scattering, more or less. The only caveat there is that the neutrino is actually changing to a charged particle when it does that. And so it exchanges a charge with the nucleon. You start out with a neutron, you go to a proton. So you end up with two neutral things, and they create two charged things that you can see in your detector. So that's the goal of this lattice calculation that I was doing, which is really a hardcore theory calculation to try to understand that interaction strength with as much detail as possible.
Okay. And that interaction strength is how a neutrino appears from a reaction.
That's how we would measure a neutrino. It's also the inverse of how a neutrino might show up. So there turns out to be a symmetry where you can reverse time. That sounds a bit silly when you say it, but the idea is that the physics works the same whether you're going forward in time or backward in time. So you can think about a reaction where you have a neutrino hitting a neutron and creating a proton and a charged lepton, they call it. Or you could think about it in the reverse. You have a neutron that's going to decay, and so that decay will create a charged proton and a lepton and a neutrino. Or you could rearrange them even more still. Rather than hitting a neutron, you hit a proton. Your lepton hits a proton and creates a neutrino. And so things have a lot of symmetries that you can really rotate things around and try to understand them a bit better in that way. And so
Can you define lepton?
Yeah, so if you think about an electron is a lepton. And so the idea is a lepton is a charged particle. It has some specific definition that really doesn't matter here. But the idea is that these particles have certain charges. So electric charge is one of them. Neutrinos are also leptons, but they are not the charged leptons, they are neutral leptons. And so there's also other types of leptons that you can think of, like a muon, which is most of the time what I'm going to be talking about. So a muon is really just a heavy electron. It has all the same properties, except it's 200 times heavier. And so really that's it. It's a fundamental particle like an electron. And so a neutrino is very much like an electron too, except that it's a neutral particle. And it does not have electric charge, so it's much harder to see.
So I asked, the charge on so the lack of charge on a neutron makes it invisible?
Yes. So it makes it invisible to detectors. So typically you need to interact somehow with the detector in order to be able to see it. So with protons, they shoot through the detector, they have electric charge, they scatter off of electrons, protons, whatever has charge as well. For a neutron, it's a bit more challenging because it doesn't have an electric charge, but it has a strong charge, as they call it. The the constituent quarks that make it up have a strong charge. So it can exchange other particles like pions, for instance, are a type of particle. And so these particles are charged and they interact with the strong force. I shouldn't say they're charged under the strong force. And so you can get interactions based on that. So you can still see neutrons in the detector, but they're harder. They're a step harder because of that. Neutrinos don't interact with the strong force either. So they're even harder, and they interact with what's called the weak force, which is, as the name implies, they are very weak. And so they're several orders of magnitude weaker than your typical electromagnetic charges. So it can be very difficult to try to measure things that are only charged under weak interactions, like the neutrinos. So in order to get around that, you have to have a lot of them. And you hope that a few interact with whatever you're trying to detect, or interact with your detector, and then you measure the things that come out of those. So if you're trying to measure a neutrino interaction, you would try to have the neutrino hit something, and then you measure the things that it hits. So it will hit a proton, it will knock it out of the nucleus, and then you can measure the proton. And in that way, you can understand what's going on with the neutrino.
Okay. And having it hit a proton is very difficult, correct?
That's right, yes. So typically we have to send billions of them through the detector all of the time. In fact, everyone has billions of neutrinos streaming through them every second, and the interaction is so weak that you'll maybe get hit by one in your lifetime.
And what are the implications of that hit?
Very little. I mean, so if you're thinking about radiation, when you go outside and you're standing in the sun, you're getting ultraviolet radiation. And so that can give you a sunburn. So you have to imagine how dangerous it would be if you got hit by one photon rather than the entire sun's rays. So it's really not going to be much. And probably you won't even notice.
Okay. So what are, well, before I ask this question, so neutrinos have weak force because they don't have, do they have quarks or they don't have quarks?
They do not have quarks. They are fundamental particles.
Fundamental particles. And what are fundamental particles?
So if you want to think about what a fundamental particle is, it really has to do with what happens when we hit them against things or shoot things at them. So if you imagine a proton or a neutron, protons and neutrons are made up of three quarks. So you have up, up, down, or up, down, down, depending on whether you're looking at proton or neutron. So if you actually shoot, for instance, photons or electrons at a proton, what you'll see is that you'll see things that scatter. You'll see that electrons scatter. And so when you measure within a certain energy range, that scattering will look like you're actually hitting not a single object, but some composite of three objects. And so you can actually detect the differences between those. If you have fundamental particles that are scattering, for all intents and purposes, they look like they are just billiard balls. So you hit one off of the other, and all the interaction is completely described by simple kinematics like that, up to going to too high of energy, and you can create other particles that mess with that. But the simple picture is that if you look at low energy scattering, everything looks like a single particle. Or
okay.
A billiard ball, essentially.
Okay. And when you say low energy scattering, you mean fundamental particles hitting each other?
Right. Yes. So by low energy, what I mean is we're keeping the velocities of the particles relative to each other very low. Now, we're talking low on the scale of the speed of light. So these are still quite high velocities, a significant fraction of the speed of light, but it is low from the perspective of the particles themselves.
Okay. And an atom would not be a fundamental particle because it can be split and broken into, so it gets hit and then it's not a billiard ball. There's particles that come off of that.
Right. So you can imagine that when you hit the atom, it actually deforms and kind of collapses on itself and goes into some other state. And so that is the types of interactions we're talking about. So it's more like a bouncy ball rather than a billiard ball, in that it will deform, it will change shape, it might break up. And so, of course, the atom is made up of protons and neutrons, and those protons and neutrons are made up of quarks. So in that sense, it's not a fundamental particle. So fundamental really means that that is the smallest particle that makes it up.
Okay. And you mentioned pions earlier. Are pions fundamental?
Pions are not fundamental. So they're actually made up of quarks as well. The pion that we typically think of, there's three pions. There's two charged and neutral. So pi plus, pi minus, pi naught. If we're looking at pi plus, it's an up and a down bar quark. So it's a quark and an antiquark pair. And so that's what we mean by meson, is this quark-antiquark pair.
Meson?
Meson is the word. I said pion before, but pion is a meson, which is a quark and an antiquark. I'm just throwing out new terminology left and right here.
Okay. Well, it's a very emerging and complex subject.
Right. Yes. I guess, what's the word I'm looking for? The informal name for all this is the particle zoo.
That's what you and your colleagues call it?
Well, this was back in maybe I think the 60s. They were doing these, what they considered high energy experiments at the time, and they were creating new particles left and right, and they didn't know how to deal with this particle zoo because they didn't have the right mathematics to describe how the particles are related to each other.
Wow. And what was the result of that particle zoo in the 60s?
So they kept creating new mesons, essentially. So they started out with the charged pions, and then they ended up creating eventually kaons, which now it's not an up and a down quark, but it's a strange quark that's mixed in there. And so you can start.
What's a strange quark?
So you have up quark and down quark, which up and down really are just nomenclature. They don't really mean anything.
Yes.
And so they started seeing new particles, and one of the ways that they came up with the mathematics to describe it was by looking at how the particles interact with each other, and some of the properties, you can group them in certain ways. And what they found from this grouping was that they really preferred to have a third quark of a different flavor, not up or down, but it was something that was really strange. So they conveniently named it the strange quark. And then later they discovered that there was another quark that was more like the up quark rather than the down quark. And they named that one the charm quark. And then there's also a top and a bottom quark. And so these are all the quarks that we know about. There could be higher ones, but it's highly unlikely.
What makes you say it's unlikely?
So there's very quantum mechanical ways of probing whether you have more particles than what you actually see. So essentially, you're measuring things very precisely. They call them electroweak precision measurements. And in this way, you can be set. They call them electroweak precision measurements.
Okay.
Electroweak referring to electromagnetic and the weak force. And if you do these types of measurements, you can be sensitive to things that are above the range of where you can actually produce them in an experiment. And this is purely due to quantum mechanics. And in this way, you can actually count the number of quarks that you expect. And what people find is that they're sensitive to things up to the top quark, and then they don't see anything beyond that. And so in that way, you can try to count what's going on. And if you want to have more quarks than that, you have to do some gymnastics to try to make them interact less strongly. And then there's some questions about whether you would expect a theory that can do this or not.
Okay. And when you say gymnastics, you mean mathematical gymnastics?
That's right. Yes. Mathematical gymnastics. So making things interact very weakly, or having them somehow do some other strange things. You can have particles mix very weakly and end up in different sectors, or you can have some other heavy particle that mediates an interaction between these particles, and it can get very weird if you're talking about things like this.
I can imagine. What was your relationship with math before you entered your graduate program? And was your undergrad program highly mathematical?
So my program was, I mean, I do have a bachelor degree in mathematics as well, in addition to my bachelor and PhD in physics. So I do have a
So
strong.
you have two bachelors.
I have two bachelors, yes.
Wow, great job.
Yeah, so I did have a strong background, and I have used it to its full extent. I mean, so you really need to have a strong grasp of calculus and statistics in order to do these types of things.
What types so is this statistics with calculus as one mathematical function?
No, so the statistics and the calculus are separated. So the calculus is how we do the lattice calculations. So if you want to break it down into simpler terms, there's the concept of an integral in calculus. And so most of the problems you would solve in maybe your undergraduate calculus course would be like 1 or 2 dimensional integrals. So something that you can compute, but maybe it's a bit challenging. So the things that we're working with are several hundreds of billion dimensional integrals, and not only integrals of variables, but integrals over functions as well. So you can think about all of the possible shapes that a function can have and integrate over that. And so that's a new concept. And that's very core to the types of calculations we're doing. We're trying to actually look at this billion dimensional integral, and that can tell us about how the particles propagate through space and through time, actually.
Wow, how does a billion times integral relate to this space-time, these particles in space-time?
Right. So the field that I'm working in is lattice QCD. And so lattice here refers to like a crystal lattice. And the lattice that we're specifically describing is all of space and time in our fictional universe. Now this fictional universe is 10 to the minus 15 meters across. So it's tiny, tiny, tiny thing.
Wow.
Maybe 10 to the minus 14. But the point is that every single spatial position is a site on this lattice. And so we are computing things that are living purely within this crystal lattice, which is 10 to the minus 14 meters across. And then even we're a bit weirder in that we require that time be periodic as well. So when you move forward 10 seconds in the future, you end up back where you started, and time just repeats itself ad infinitum. Now,
wow.
I was saying 10 seconds as just a random number I pulled out of my head, but it's more like probably a nanosecond or smaller scale.
Wow. What's the reason for the 10 to the minus 14 size lattice?
So there's a couple of reasons. One of them is that you want to keep the lattice on the same scale of sizes as the particles you're trying to describe. So if we're looking at nucleons, you want to keep your lattice at least the spacing between your lattice sites smaller than the size of that object. So that would be a nucleon. A nucleon is about, again, 10 to the minus 15 meters. So you want to have your lattice be roughly that size. And so we even look at 10 to the minus 16 meters spacing between each of the sites of the lattice. The other side, the total box size, where we're looking at 10 to the minus 14 meters, that's purely limited by how much computing power we have.
Wow.
So each of these snapshots that we take of our lattice are several terabytes of data. So we have to be very careful about how big we make these things. And if they get too large, we can't fit them even on the largest supercomputers.
Wow. How does that feel to know that you have this and it's extremely it's so computationally expensive that even the most advanced computers today can't solve that yet?
Yeah, I mean, it's very fun. I mean, at some points I've had several hundreds of terabytes of data that I've been manipulating and playing with. So it's fun to get on all these computers and to be able to run on some of the best architecture out there. Some of these top 10 computers in the world.
Wow. So what is it like to run a computation on one of the top 10 computers in the world?
So typically you have to wait in line a lot.
Yes.
So they have some sort of queuing system where you would come up with your job, you describe the computation you want to run, you have all the scripts that would do this computation, and then you put them in line. And then you go home, you close out your computer, go away, don't think about it for a while, and you come back and you look and see eventually your results will have run and you can go analyze the data. So it's all handled in some democratic way. I mean, everyone gets allocated some certain amount of computing time and then they get to use it how they want. And so when you submit the job, you'll get some number of nodes based on how many you request, which is just essentially compute nodes, the same things you have in your desktop. And so you'll get these for some amount of time, you'll do your computation, and then you exit out and the nodes go to someone else. And so in that way, you're sharing the nodes with a lot of other people. Everyone gets computing time. The computer gets used pretty much constantly all throughout the year. So these things never get a break.
I bet.
Yeah. And so some of the scales of computing time we're working with are quite large. So specific to my project, we've had some computing time which ends up being several tens of millions of core hours, which if you translate this to something more manageable or easier to think about, if you were to run the same simulation on a single core of a single computer, then this kind of simulation would take something like 10,000 years to complete.
Wow. But
So
these computers are much more powerful.
yeah, so the idea is really you're using brute force. So rather than doing it on a single core, which would take several millennia to compute, you would run this on several computers at the same time. And so you have them all plugging away, doing similar computations all at the same time. And so like it's easier to build a building having 10 people do it versus one person. It's easier to do a computation having 10,000 cores doing the computation rather than one core.
That's a very interesting dynamic, that it's really just brute force. And I believe that this is what I've heard, that the most powerful neural network algorithms are really just the ones with the most nodes and the most connections between nodes as well. And it's similar in the sense of it's just more nodes, more connections.
Yeah, certainly having more helps. I mean, if we had more, we would simulate bigger lattices, make the lattice spacing smaller, and everything would be very easy for us to do. But unfortunately, our resources are limited, so we have to make do with what we can. So you just have to assess whether your problem is able to be done in the resources you have and figure that out. Same thing with neural networks. If you can actually simulate and have a neural network that's set up with as many neurons as possible, that would be ideal.
Yes, that would be. We just don't have the capacity outside of our skulls.
Right. Yeah, I mean, even sometimes training these neural networks is difficult because you have to make sure that all the interactions between the neurons are described right. And so that requires some amount of fitting to actually come up with, or to train your algorithm, as they call it. And that training can be quite computationally intense too. So if you keep inflating your problem, you make it harder on yourself.
Yes, I was going to ask, did you have to do any of that, any, trimming of your algorithm based on results, or how did you determine that this was actually like 10 to the negative 14 was enough computationally and you couldn't do any more, and if you did less, you wouldn't be taking full advantage of the capacity available?
Well, in some sense, I'm standing on the shoulders of giants. So people before me who have worked in the field have done a lot of simulations before. And so there's been a mountain of work that other people have done to try to study whether they could even do these types of simulations. And so it was previously thought that you needed to have computers that were many, many times better than the computers we have in order to do these types of calculations. And so from dedicated work by the entire field, people eventually figured out that no, in fact, the computers we have today, or even a decade or two ago, were sufficient for doing these types of calculations. Now, granted, the first calculations were on lattices that had maybe 8 sites total, but by 8 sites, I mean 8 crystal sites in our lattice. So this really only has 2 positions of space-time in each spatial direction. But over time, things have gotten much more sophisticated and much bigger.
And those 8 space lattices were really done on normal desktops, correct?
At the time, yes. But desktop may have changed in definition. So, I mean, some of these computers were these big entire room computers back in the day. I mean, this has really been benefiting based on Moore's law. So the exponential growth and how many transistors you can fit on a silicon chip is really helped this field quite dramatically.
Yes, and very recently too.
Yes. Yeah, so currently calculations are getting to the scale of they call it the exascale, which is just how many computations, just multiplying 2 numbers, can you do per second. And so they're talking about floating point operations in several orders of magnitude higher than what was done previously. The amount of computing time we have these days is staggering.
And it seems like it's very soon going to become obvious how staggering it is. And because quantum computing is still a bit in its infancy, and you're taking advantage of it. What do you think about quantum computing?
So quantum computing it turns out to be quite a fad right now. I guess something like maybe 4 or 5 years ago, something like that, suddenly quantum computers started to show up, and the government said, we want quantum computing. So they started throwing money at it, and people were like, of course, yes, I will take more money. So there's been a lot of recent interest in quantum computing. And so a lot of people have completely switched topics and gone over to quantum computing. And it's very exciting, but currently some of the problems that people are dealing with are that essentially your signal just disappears. So either the system isn't quite cold enough, and so you end up getting some sort of thermal motion that screws up your calculation, or even a cosmic particle comes in and hits your quantum computer and changes the answer that you're looking at.
Really?
Yeah, so people are sensitive to that. Quantum computing still has some ways to go, but it's still exciting, and it's interesting to think about some of these topics. I have, I guess we'll say, a hobby-like interest in it, but I don't do anything with quantum computing right now. And lots of the problems we would like to do with quantum computing, we still don't know how to do.
What do you mean by that?
So the way that you would set up a problem in a quantum computer is very different from how you would think about it classically. And so, for instance, if you want to copy a number, in a classical computer, this is very easy. You just say this string of bits has to equal this string of bits. And so you would take the information from those and copy it over, and everything would be fine. In quantum computing, there's something called a no cloning theorem, which says that you cannot clone a state. So if you want to copy something from one spot to another, it's impossible. So you need to have some other way of doing that, or to get around this somehow. And so that puts some serious limitations, and people really don't know how to think about these problems yet. So this is, I would say quantum computing is at the stage right now where computers were, I don't know how many years ago, playing with transistors and trying to come up with something that could maybe compute 1 + 1 = 2.
Got it. But it's way more expensive to do that tinkering than it was with just a transistor or two.
Oh yeah, but I mean the types of problems that you can accomplish with it are very different from what classical computers are. So for instance, if you want to do prime number factorization, which is very important to how modern cryptography works. So if you want to send a bank transaction through your computer, it relies on this. So it turns out this problem is very easy for a quantum computer. You can factorize numbers very simply and much faster than you could do on a classical computer. And so it turns out that problems like this are very well suited for quantum computers. So it's a different mentality even than the classical computers. We're solving entirely different problems, and right now we really don't know what types of problems we can solve with it.
That's exciting for people that are involved in that field.
Right, yeah, exactly. And so a lot of people in the field are currently treating this as kind of the, this is very early stage, so anyone has the potential to become like a really famous person in the future, just by being quite clever and coming up with some sort of new theorem that helps us with quantum computing.
Wow. And so you're in your postdoc now.
That's right.
And what do you want to do once you're finished with this program?
Yeah, so I mean, there's still way more to do. I mean, I had mentioned that I have like 12 projects that are ongoing, but so I'm not only computing neutrino physics, this scattering off of a neutron, creating a proton, but also there's more complicated interactions that you can do. For instance, neutron scattering with a neutrino, and rather than creating a proton, it creates a neutron and a pion. So something like that. And so these turn out to be very important for neutrino scattering as well. And they're even harder to measure than this initial interaction that I was talking about.
What makes them harder?
So part of the reason is that you have to go to a higher energy. And you have to be high enough energy to create this pion. There's also some complications with measuring them in the experiment. So typically, like I said, you have this proton that comes out when you do this simpler interaction. And so you can see the proton. But in this nucleon-pion type interaction, you end up with typically one charged, one neutral particle. And because it's a neutral particle, it's harder to see in the detector. So you end up having to do some more gymnastics on the experimental side to try to figure this out.
Wow. And so, no, continue.
I think I was done there. So go ahead.
So you are running simulations of neutrino collisions and various other fundamental, but also non-fundamental particle collisions, correct?
Yes.
But there are a few physical experiments being done on this exact science as well.
Yes. Again, the experimental side always comes with its challenges. In this case, it turns out to be a very dangerous experiment to do. So if you want to interact with a neutron, typically the way you would do this is you would put the neutron in a nucleus. So deuterium is the example. Heavy water, or in this case, it's even hydrogen, where the proton in the hydrogen atom has an extra neutron attached. And so, as you know, hydrogen gas is very explosive. This is what caused the Hindenburg to go up in flames. And so what we want is we want a high statistics experiment, which means that we have to get a large container of hydrogen and stick it underground in some cavern. And so any little spark from all the electronics equipment that we have around it can cause a huge problem. Completely destroy the experiment, lose a lot of deuterium, which actually is quite expensive as well.
What is deuterium?
So deuterium is this hydrogen atom where you have the proton and the neutron bound together. So it's the simplest type of atom with an extra neutron attached. And so hydrogen makes up most of the weight of the sun, most of the mass of the sun. And these are just an extra step beyond that, adding this extra neutron, which is really what we want for this type of interaction.
Okay, what's the reason? What's the reason you'd want that extra neutron for the interaction?
So really, quantum mechanics tells us that we can't interact with the proton because we can't conserve charge if we do that type of interaction. So charge conservation is one of the fundamental principles of physics, and so we have to obey it. But proton interacting with a neutrino, it turns out it doesn't interact in the simple way that we're trying to measure. You can do more complicated interactions that will still conserve charge, but aren't the type of thing that we're trying to look at. So it's essentially trying to solve the wrong puzzle. That's kind of the gist of it. So for instance, this neutrino interaction that takes you from a proton to a nucleon pion state, that's something that's allowed when you have a proton interaction. But for the interaction where you only have a nucleon coming out and none of these pions, that interaction does not happen if you have just a proton.
Okay. Are these reactions, are these oscillations?
So these interactions are not oscillations. Oscillation is a different principle. So the idea is that you would create one of these neutrinos, and so it's propagating through space. It's going nearly the speed of light, coming out of the sun, for instance. And so when you create it in what's called a flavor eigenstate. And it's just jargon, but it means that when you created it, it came from an electron interaction, for instance. An electron hits something, it creates an electron neutrino. And so that neutrino is propagating through space. It turns out that the propagation is controlled not by the flavor eigenstate, but the mass eigenstate, so how much it weighs. And the electron neutrino is a quantum mechanical superposition of several different mass eigenstates. And so each of those mass eigenstates will propagate with a different speed, which are all effectively the speed of light. So we can't really tell the difference between them anyway. And then when it gets to the detector, it is not in quite the electron neutrino state that it started in. It's in something different because of some sort of quantum mechanical interference that happened between all these different mass states. So when you get to the detector, you can actually measure something else, like a muon neutrino. Like I said before, the muon was one of these heavier charged electron type particles. And so when we look at the detector, we'll see something like muon neutrino, even though we started with something that was an electron neutrino, which was something entirely different. And so we call that property oscillation because what happens is that you will start out in one state, you will go to something that is some mixture of states, and then you'll come back to the original state that you started in, and you'll go out of it, and you'll come back, and you'll go out and come back. And so it oscillates back and forth between what probability is associated with what state. And so we can actually measure those probabilities, and in that way we can understand the physics behind this type of oscillation between states.
Okay. And running theoretical simulations on neutrinos, oscillations are simply one of the projects you do. It's not revolved, your work is not completely revolved around oscillations. There are other particle interactions that you work with and you simulate as well.
Yes, that's right. So for instance, one of the other projects that I do is pion scattering. So this turns out to be very useful for this muon G-2 project that is ongoing. So there was a recent experiment where they're trying to update this because there's some sort of tension based on what we expect versus what we measure. And so the calculations that I can do on these computers actually help with trying to understand that discrepancy there.
What discrepancy?
So this is the muon G-2. Is what it's called. And so the idea is that a muon has something which is a magnetic moment. And so this is just a fundamental property of the muon. And if you look at what's causing this anomalous, quote unquote, magnetic moment, it is the fact that you can have quantum interactions which change the magnetic moment away from the value that you would expect from a classical theory. And so those types of extra interactions are just really quantum mechanical particles popping in and out of existence. And so one of the particle combinations that pops in and out is a pair of pions. So you can have pi plus, pi minus, or 2 pi knots. And so your muon will create a photon. That photon will turn into a 2 pion pair, it'll go back to a photon, and then it will interact with the muon again. And so this can actually change the magnetic moment that you measure. So then there's an experiment to try to measure this magnetic moment. And so what you do is you put a bunch of muons in a ring, you apply a magnetic field, and then you can look at how the muon essentially processes in this magnetic field. So it's spinning like a top, and you measure what direction that spin of the top is facing. And so if you measure this and you compare it to what we expect from all the theory that we have, all this mathematical work that people have done, those two disagree. And they disagree by quite a significant fraction. So the answer is about 3 standard deviations, which is just a rough estimate of how much error we expect on these measurements. So it's not quite at the scale of where we say this is a fundamental discovery of a new property, but it's also not at the statistical level that we would expect from some sort of measurement. I mean, it's still quite a large discrepancy based on what we should expect. So we're a bit cautiously optimistic. Maybe this means there's some new fancy physics out there that we can later discover. Maybe it's just a statistical bias, although that's unlikely. Or it could be some sort of systematic effect that we have that we still need to understand. And so doing these calculations helps with trying to understand the latter of those. Essentially understanding, is this some systematic associated with how we've measured this from the past, or how we've computed what the theory should be.
Wow. So in that sense, modern mathematicians have a tool in these quantum computers? Because can they at least somewhat verify if this is false? And is that what you just described, that discrepancy between a simulation and what was theoretically believed?
So I would say that's classical computers, not quantum computers. But yes, I mean, so the computations we're doing really are helping with this. And I should stress that the simulations we're doing are really based on the fundamental theories of what we expect to happen in nature. So we take a few simplifications, but they're simplifications that we can actually control. So we can remove these effects and understand what would happen in the real world, the physical world that we all know and love. So yeah, all of these big simulations are really helping with trying to understand this. And this really helps with trying to understand specifically these interactions where you're involving quarks and gluons and all of the strong force interactions.
How did you first become interested in quarks, pions, and neutrinos and quantum physics?
I mean, I think this was just from reading about these things as a kid, really. I mean, you read about Einstein, everyone knows him. And so you find out he's doing all these cool things with just pen and paper. And I was like, I want to do that. So I started down that career path, and it's just gotten more and more fun as I've gone down it. I mean, this is really a job that I enjoy. So I have no qualms with being in this path. Even though these are very hard problems, it's like opening up the newspaper and going to the Sudoku and solving that one.
Yes, except no one solved this one yet.
No one solved this one yet. This is some million by million Sudoku, and you can be the first one to solve it. And even this allows for some amount of being clever as well. I mean, lots of the tricks that we use are just some clever idea that somebody had, and they applied it and it worked well. And so everyone else adopted it, and now it's commonplace.
Yes, and I think people tend to think about mathematics and physics being very rigid, but in order to discover new things, traditionally mathematicians who have been very innovative were very imaginative people. And
That's right.
They weren't so structured as our traditional thinking today would have us believe.
Right. Yeah, so there's a lot of room for being clever in mathematics, and even more so in physics, because physics is not quite as rigorous as mathematics is, but it's still very rigorous. But I mean, in physics, you're allowed to do approximations that you're not allowed to do in mathematics. So that's the mindset that I'm coming from. So for instance, you can say, well, 99% is good enough, so let's come up with something that can compute 99%, and that will be good enough for our purposes. And in that way, you can do a lot of physics by just computing the 99% rather than the 100%.
Okay, but in mathematics, it's 100%.
100% all the way.
Wow.
But that can be very challenging and can be quite a damper if you don't know how to solve it without going through all of the work of that.
I can imagine. What's the reason that physics is not also 100%?
I mean, so really we want to solve practical problems. And so if you want to solve a practical problem, you need a practical solution for it. And if you're stuck on trying to prove everything with 100% accuracy, then you're going to be stuck for a long time. I mean, mathematics, there's still some very challenging problems to get around. And even I could even be so mean as to say in mathematics, there's something called Gödel's incompleteness theorem, which is essentially saying that there's some things that can be right, but you can never prove that they will be right. And you can prove that they will never be proven.
Wow.
So,
is there an example that you have in mind?
No, I don't have an example. But so even proving so this doesn't necessarily have a proof that it can't be proven, but I think the consistency of mathematics, even saying that 1 + 1 = 2, and saying that you will never end up with some answer that intuitively we would think is incorrect. I think that even that cannot be proven using mathematics so far. You essentially have to start with some axioms, which are essentially saying you start with assumptions in mathematics, and then you can prove everything else. And you can start with 6 axioms and develop all of the mathematics that we have today. But in order to prove that those 6 axioms are consistent and will never produce something that doesn't make sense is so far out of our hands.
Got it. And so that is something we cannot prove. But
I'm not saying that it can't be proven. It's just that it seems to be that it's something out of our hands and we can't figure out how to do it. There's a difference there. One is saying it's impossible. The other one is saying we don't know how to do it.
Got it. And we could stumble upon it.
We could stumble upon it. I mean, it could happen tomorrow that somebody proves it, and then we'd all go out and celebrate, have a bottle of champagne. But I sincerely doubt that it will be solved anytime soon. And it could just be that it's in one of these problems that you cannot prove.
Wow. And when you say 6 axioms, are there actually 6 axioms of mathematics?
I mean, you can come up with more, but there's... don't ask me to recite them off the top of my head.
No.
It's something like 5 or 6, but the idea is you start out with numbers, so the typical integers that you would think about or something like that. You can even go more abstract than that, and you can start out with something like saying that A + B = B + A. That's one of these properties where you can say that the operations can be commuted, and that's one of the axioms you can start out with. And based on what you assume, you can end up with some really interesting properties. So for instance, if you assume that all of the angles of a triangle add up to 180 degrees, that's very simple thing that makes a lot of intuitive sense. But what happens if you assume that the angles don't add up to 180 degrees? And so then you get into what they call non-Euclidean geometry. And so that would be, for instance, describing the surface of the Earth. If you start at the North Pole, you go to the equator, then you turn to your left by 90 degrees, you walk along the equator for a while, and then you turn to your left by 90 degrees, you go back up to the North Pole, you can end up with something where you have a triangle that has the sum of its angles at 270 degrees.
Wow.
It's not saying that's wrong, it's just saying that it's a different type of mathematics. And it has its own properties that you have to be able to account for.
That's a very interesting and easy to digest way you put that.
Yeah.
Different frameworks of assumptions are for different forms of mathematics to solve different problems.
That's right. Yes. And so that turned out to be a very challenging problem back in the day, back in, I think it was the 1800s, when they were trying to think about these problems and come up with the mathematics formulation. They posed this question of all triangles have to sum up to 180 degrees. And then somebody said, well, do they? And a whole new branch of mathematics was started.
Non-Euclidean geometry.
That's right.
Do you know what Euclidean stands for?
So Euclid is a person. He was a famous mathematician.
Okay.
I believe back in the ancient Greeks. Don't quote me on this. I hope that's right.
Okay. He's not Euler.
Not Euler. I think the pronunciation there is Euler.
Euler.
I've heard both
right.
though. Doesn't matter anyway.
Okay.
Famous mathematicians.
Okay, got it. Wow. And so you mentioned a few minutes ago, physics, you want practical uses to be derived from it. What practical uses do you see or envision or want to see come out of your work and your team, your colleagues' work?
Right. So that's a question I get asked a lot. And so the answer is, does it really matter if we understand neutrino oscillation? And the answer is probably not in our lifetime. But there's a lot of other side benefits that come from this. So for instance, we're heavy users of computers. And so a lot of my colleagues actually have partnerships with, for instance, NVIDIA or Intel. And so they actually help develop the hardware that gets used and ends up on the consumer market. So a lot of the innovations that come from the type of abuse that we have of this hardware for our own purposes ends up down the line getting put into gamer cards or other faster, better processors that get used in an everyday computers. The specific sorry, what am I thinking about? The accelerators that we build, there's a lot of use of superconductors. And so it could be that some of the breakthroughs that come from trying to build better superconductors, excuse me, to have better accelerators ends up somehow in the consumer market. Maybe there will be a room temperature superconductor, and that could revolutionize how the energy grid is set up.
What is a superconductor?
So a superconductor is a specific property of a material. So typically you have to get the material to be very cold in order to get superconductivity. But the idea is that when you get it into a superconducting state, suddenly all of the electrical resistance drops to zero. And so you can have very efficient transfer of energy through electric interactions. So you can get electrons from point A to point B with very little resistance. And so that's effectively what's going on, is that, well, in a practical sense, if we have this for an energy grid, this means you can transfer power from your power plant to whatever city you want all the way across the US with very little losses. Whereas these days you have to go through power stations where you build up the power again and then transmit it, and that all comes with losses. And so that really confines how far away you can send your electricity before you have to have a new power plant somewhere else. So something like that could be very important for practical people. And this is really coming from the types of research, this hardcore experiments that we're doing, that we're putting a lot of effort and money into.
Absolutely. A lot of the mathematics on prime numbers was solved, I think, before 1900, and that mathematics is used in the cryptography that completes our bank transactions.
Oh yeah, yeah. I mean, even the example of lasers, when they were first discovered, I think that people were like, how is this ever going to apply? But now you have lasers in everything. In your desktop computers, this is how they read information off of a disk. And you can think of all number of different reasons for using lasers. And this really came out of some very simple technology that people were just playing around with.
It's an exciting time, I think, for science.
That's right.
Well, Aaron, I think we're at time. Are there any last words you'd like to say to our audience?
I should just say, if you're interested in science, you should absolutely pursue it. I mean, there's a lot of people out there who just doubt themselves, and really, if you want to do it, you should just do it. And it doesn't matter what other people say. If you try hard enough, you can make it. People give up too easily, I guess is what I'm trying to say.
My guest today has been Aaron Meyer. Thanks for coming on the podcast, Aaron.
Yeah, thank you for having me. It's been a pleasure.